Welcome back, ladies and gentlemen, AutoCAD programming aficionados. Today, I'm going to explain to you all about 4x4 transform matrices. Transform matrices are used in the architectural windows program in order to transform the points of the 2D LW polyline rectangles that are used to place windows from their entity coordinate systems into the 3D coordinates of the world coordinate system so that a window can be drawn in that location and orientation. Well, basically, 4x4 transformation matrices are very useful in many industries, such as 3D video games and robotics. Why 4x4, not 3x3? Because a 3x3 matrix can only do a 3D rotation of an object around its origin, whereas a 4x4 matrix can accomplish an arbitrary 3D rotation around an object origin as well as a 3D translation, which are the only transformations that can be done on solid objects. Transformation matrices can be used for other things as well, such as projections, but that's beyond the scope of the architectural windows program and this video. How does a transform matrix do this? It's because of the magic imparted on it by its fourth row. And as you can see here, here's the fourth row of a transform matrix, and it's got the 0, 0, 1 on its lower row. As well as when you put points in here to transform, you got to put a 1 on the bottom here. And the reason why this works out so well is because if you do the matrix math, all right, first you get this here, okay, which is just the top row multiplied by this vector, followed by the second row and the third row and the fourth row. And it comes out to this here, which, as you can see, this goes straight down to here, and this goes straight down to here. Same for that, and then you get this strange one here. And what this equals is basically this. It's a unit vector multiplied by x, a unit vector multiplied by y, a unit vector multiplied by z, plus this t vector, which is the translation vector that you want to translate the object by. And so I'll show you what I, j, and k is. It's basically the axes of the coordinate system that you want to map an object to. In the case of the architectural Windows program, it's those rectangles which represent where you want to put a window. And for demonstration purposes, I got this polyline which represents a rocket ship. So imagine you're a video game programmer and you got this object, it's a rocket, and you've gotten it described in points with in terms of its own object coordinate system, uh, which is static to the object. And in this case, is also the world coordinate system here. All right, is also the world coordinate system. And so, what a video game programmer will want to do is he'll want to map this object over to the coordinate system where the rocket ship is at any point, so that it can be projected onto the screen, along with all the other objects. And so uh, we want to have this rocket pointed along this green vector here, and in the IJ plane. The I unit vector is the x-axis of this other user coordinate system. The j unit vector is the y-axis of this other coordinate system, and the k vector is the z-axis of this other coordinate system. And of course, this ball here is the origin of that coordinate system. So fortunately for you all, I've written a program which does this um, using 4x4 transformation matrices. I got a program which figures out the transformation matrix of a user coordinate system icon, and it finds out what the points are of a given polyline, and then is going to project this polyline onto this coordinate system here. And I got it loaded up right now. Where'd it go? There it is. It's called Transform Polyline Points. So I'm going to run this, and I'm going to show you how it works, and then I'm going to show you exactly how it works internally using 4x4 transform matrices. So I'm going to run the program. First thing it asks me for is to pick the UCS icon block. And look what it did. It actually wrote out the transform matrix of this coordinate system. And now it wants me to select the polyline. So I'm going to select this polyline here, and watch, it's going to draw it over here, and it's going to put the points of the original polyline over here, and then it's going to put an equal sign, and it's going to put out the transform points. So boom, there it is. As you can see, it transformed those polyline points into the other user coordinate system, and it did the math. It put out the math here. And so now what I'm going to do is I'm going to do it on a simple object so you can see exactly how the program works and how the math works. Really, I'll show you how the program works maybe as well. In any case, so I'm going to use a much simpler example. The transform I'm going to do is I'm going to do a 45-degree rotation around the z-axis and a translation of 5, 2. Here's the 5, here's the 2, and here's the 45-degree rotation. As you can see, is a user coordinate system that has been rotated 45 degrees. So we're going to take this object here, we're going to rotate it, and then we're going to translate it so that this object here is going to fall into this position by the time it's done. And so I'm going to use the same program on this uh, on this triangle right here. So first of all, I am going to turn off this diagram here. I'm going to put that shape back on here. And so it's very simple. This is 1, 1, this is 2, 1, and this is 2, 3. Those are the points of this triangle here. So now I'm going to run the same program. And so I'm going to pick the icon block here. There's its transform matrix. It's much simpler, as you can see. We'll go over that in a second. And now I'm going to choose this triangle. And look how simple it is. Now we're going to be able to see that the mathematics works out just fine. First of all, I'm going to show you that the points of this triangle are correct. There's the 2, 3 point, there's the 2, 1 point, and there's the 1, 1 point. The z coordinates are all 0. And so there's 1, 1, there's 2, 1, and there is 3, 2. And now let's take a look at the transform matrix, okay? And if you take a look up into the upper left corner of the transform matrix, what do you see there? You see the transform of a 45-degree rotation. 0.707 is a cosine of 45 degrees. And this 0.707 here is the sine of 45 degrees. And this negative 0.707 is the negative sine of 45 degrees. And this 0.707, once again, is the cosine of 45 degrees. And that is, by definition, a, it's a two-dimensional rotation of 45 degrees around the origin. And then if you take a look over here, there's 520, and that is exactly the offset. There's 5 here and there's 2. And now if we take a look at the results, when you rotate this object 45 degrees, this point right here, 1, 1, gets right above the origin. Okay, so look right here. If you go over to look at this point right here, it is exactly 5 on the x-axis, and it's 3 something on the y-axis. And so that conforms to this output here. It's 5, 3.414. That's this point right here. And then 5.7, 4.1. That 5.7, 4.1. That's this point right here. And then that last one, 4.2, 4.3, 5.5. That's this one right here. So it has successfully mapped this example. It has a 45-degree rotation around the z-axis and a 5-2 translation. But just to show you that it'll work in any angle, at any angle with any object here. Oh, hold on, I'll go back to 2D here for a second again. I'm going to transform another shape. I'll transform this shape right here. Still in the XY axis of the world coordinate system. And I'll run that program again here. Transform polyline points. We're going to pick the same UCS icon block. Now we're going to select this polyline here. And as you can see, it has worked. It's in the same XY plane, and it is rotated 45 degrees. Now, just for fun, what I'm going to do, well, I think I'll erase these guys here first. And now what I'm going to do is I'm going to bring out a more arbitrary user coordinate system. We're going to say goodbye to UCS1 and hello to UCS2. All right. Oh, hold on. So let's go back and map this simple triangle, this much more arbitrary user coordinate system. So I'll run the same program again. I'll pick this UCS icon. As you can see, it's much more generic here. And we'll choose this right here. And as you can see, now that output is once again in the XY plane of this alternate coordinate system. And now just for fun, so that obviously worked here. Here's the transform of that coordinate system. It's at 5, 2, 3. As you can see, it's 3 high, so it's got the correct translation. And look at these numbers here. Those represent the axes. For example, the x-axis is 0.119933,338, and that's that one right there. If you can see that, it's 0.119.933, which means it's mostly in the y-axis direction, as you can see there. And then 0.338, which means it's a little bit in the z-axis. So as you can see, what I have taught you is true. And just to prove that it works in all 3D with a with an object in another plane other than the XY plane, we'll we'll transform this shape 3 here. As you can see, this here is in another plane. It's in the XZ plane. And so we'll run the program again. And as you can see, it has been transformed successfully. This here is in the XZ plane of this coordinate system. All right, I think that proves what I've told you about 4x4 transforms, exactly how they work. Just to go over it, let's see. Basically, what happens is, oops, 4x4 transform matrices work because all it does is it takes the x, y, and z coordinates of all the points of an object, and it takes the x-axis unit vector of the alternate coordinate system and it multiplies it by x. It takes the y-axis unit vector, j, and it multiplies it by y. And it takes the z-axis unit vector, k, and it multiplies it by the original z-coordinate, and then it adds the translation vector. And that's really all it does, and it's all packaged up in this 4x4 matrix. And the math that you see here is enabled by this magic row 0, 0, 0, 1. And then, of course, you got to put a 1 at the bottom of the points that are to be transformed. And, this shows you just 1 point, but you could have, 10 points. You could have 20 points. You could have 1,000 points. Just extra columns of this matrix, matrix here. And as you can see, the math works out. And yeah, that's about it. Thank you so much for watching to the end of the video. Please like this video and please follow this channel. I really appreciate it a lot. And I guess I'll see you on the next one. Have a great night.